Section 12, per class IOU analysis. Now, let us look at the best model and look at per class performance. Let's run cell 12. Look at this bar chart. This is far more useful than a single MIOU number. You will see sea lake and forest have highest value 4.99, while permanent crop has 4.90. This chart tells you exactly what to do next. If highway IOU is low, try class weighted loss from Capstone Challenge 3. If river IOU is low, try attention unit from section 6. If all classes are low, something is wrong with your data split. Check it first. Section 13, visualize predictions. A number is not enough. Let us actually look at what the model predicted. Now let's run cell 13. Three columns: left, the original Sentinel-2 image; middle, the ground truth mask; right, what our unit predicted. For example, annual crop, pasture, and residential area. Section 14, real Sentinel-2 data loading. Eurostat JPEG tiles were great for learning, but when you move to a real project, for example, mapping the Kurdistan region, you will work with the real Sentinel-2 GeoTIFF files from Copernicus. Three important differences from Eurostat JPEG. First, 16-bit values instead of 8-bit. Second, 13 bands instead of 3. And third, embedded georeferencing. Let's run cell 14 NDVI visualization. Look at these three images. Original RGB, approximate NDVI, NDVI threshold map. This is why we never use Kalajita on satellite imagery. If we randomly shift the brightness, we change it near and red independently. The NDVI becomes physically meaningless. We would be training on fake data. Section 15, GeoTIFF export. Now we turn our prediction into something a GIS analyst can't actually use: a georeferenced GeoTIFF. What makes a GeoTIFF special compared to a regular image? Two things. First, the CRS, coordinate reference system. Second, the affine transform. We write a single band file, not RGB. Why? Because QGIS reads the integer class index and applies its own color ramp. That way, the map is editable and has a proper legend. Now let's run Cell 15, export GeoTIFF and display final comparison. Look at the 3-column view, original sentinel image, ground truth, our unit prediction. The prediction.tiff file is now saved in your project folder. It is a real spatial dataset. You can open it in QGIS right now. Section 16, opening prediction.tiff in QGIS. Let us open the result in QGIS. This is the moment that makes everything real. Let's open QGIS. Step 1, layer menu. Add the raster layer. Browse to prediction.tiff. Open. Add. Displayed as black. Step 2, right-click on the layer, properties, choose single color. The class is annual crop. Section 17, capstone challenges. We are almost done, but I want to leave you with 5 challenges that will take you from this learning exercise to a professional grade pipeline. Challenge 1, 13-band Sentinel-2. Download the full multispectral Eurosat version. Change in channels to 13. The extra bands, especially near and red edge, carry much more information about vegetation. You should see 3 to 5 MIOU points improvement. Let's run cell 17A. Challenge 2, deeper encoder. At the 5th encoder level with a 1024 channels, the model goes about 5 times deeper. For complex sense, with the many classes, deeper model is almost always win. Let's run cell 17B. The model got from 31 million to 124 millions, around 4 times deeper. Challenge 3, class weighted loss. We count how many pixels belong to each class in the training set. Classes with fewer pixels, like highway, get higher weight in the loss. The model is forced to pay more attention to them. Let's run cell 17C, challenge 3. Look at the weights. Pasture get highest weights because it has fewer tiles. We train with this weighted loss and compare your pasture IOU before and after. Challenge 4. Pre-train ResNet 34 backbone. Instead of training the encoder from random weights, we start from ResNet 34, pre-trained on ImageNet. The encoder already knows about edges, textures, and shapes. We just need to teach it the geospatial part. This is called transfer learning. Expect 5 to 10 MIOU points improvement over training from scratch with the same number of epochs. Let's run 17D challenge 4. And finally, challenge 5, real pixel level datasets. Eurosat used a single tile level for all pixels. Real projects need pixel level annotations. Here are the best open datasets for that. Let's run challenge 5, cell 17E. Dynamic EarthNet, daily Sentinel-2 with real pixel labels, pasties, agricultural time series with 18 crop types, SpaceNet 2, building footprints from high-resolution imagery, all free to download. So, you started this lecture knowing how to classify a satellite tile. Now you can label every pixel. You built a unit from scratch. You trained it. You evaluated it with a MIOU. You visualized the results, and you exported a georeferenced GeoTIFF that opens in QGIS. This is the complete pipeline used in professional land cover mapping. The same logic behind the ESA world cover product. The same logic behind FAO land use maps. Pick one of the 5 challenges and try it. Come back and share your results. I want to see what MIOU score you can reach. Thank you very much for you following along. I will see you in the next lecture.